So before I hit record, I did my action at a distance rant. Let's talk about this. So let's talk first of all about gravity field. If you have a big planetary mass, what it's really doing is it's sending out invisibly in all directions, write those in, like sort of like the tentacles of an octopus in all directions. It's sending out an invisible gravitational field. Now that gravitational field just sits there dormant. When is it detective? When another mass enters that gravity field, what direction will little m feel a force suddenly? It'll feel a force in that direction. What's applying that force? The gravitational field emitted by the mass. In fact, if you wanted me to include a direction for gravitational field, I would even put arrows like that. Now, this needs to be a three-dimensional picture, but we'll just do a flat two-dimensional picture. All objects with mass are extending out, like the invisible tentacles of an octopus in all directions, a gravitational field. Example 1 says, fill in the appropriate relationships. So we have the force of universal gravity, big G, big M, little m over r squared. Then it says definition of gravity field. I'm going to come back to that. I want to talk about the third line, gravitational field as a ratio. We said as a ratio, the gravitational field was the gravitational force per kilogram. That's the one that I gave you on your formula sheet. From that, I was able to go back here and say, oh, little m would cancel. Now I can give it to you as an actual equation. It's big G, big M over r squared. I have two ways to find the gravitational field, Adam. I can find the gravitational field if I know the planet and how far away I am. Or I can find the gravitational field if I know how hard the planet is tugging on a given mass, even if I don't know where the planet is. This was the Physics 11 version I gave you, because get the obvious one, mg. This is the universal one. Oh, what are the units for gravitational field? What are the units for force? Except also, this is force divided by mass. What's F divided by m if F equals what? This is also an acceleration. It must also be meters per second squared. Has to be. So I can ask you to find the gravitational field strength in two different ways. Jazz and Deep, what's A asking me to find? What's B asking me to find? Isn't this the same question? You know what? Let's do part A right here. Let's draw a little line down the page. Let's do part B right here. Oh, got someone walking in late. Got to interrupt. I didn't want to do that. Got to interrupt my... No, I don't want to do that, Mr. Dueck. Got to interrupt my equation. Geez. Interrupt my recording. So we have two ways to find gravitational field, Jazz and Deep. What did they give me in part A? What's this 8? What are the units next to this 8.38 times 10 to the 6th? So which one of these two versions am I going to use? Be stupid obvious. The one that has the same word you just said. Yeah, okay. So for A, I can find gravitational field strength by going big G, big M over R squared. It's going to be big G, 5.98 times 10 to the 24th, all divided by 8.38 times 10 to the 6th. Don't forget the squared. I know on Earth it's 9.8. I know it gets smaller as you get further, so I'm pretty sure you're going to get an answer smaller than 9.8. What do you get? This is fairly high up. I won't be shocked if you're in the 4, 5, 6 range. What'd you get? On your calculator as you're typing. Yeah, you. I won't say your name for YouTube, Joseph. That would be... Oh, shoot, I just did. Jacob, what'd you get? 5.68 newtons per kilogram. 5.68 newtons per kilogram. And I could figure out this was the version to use. Yeah, Jazz and Deep, kind of stupid obvious. Oh, they gave me a radiant meters. Okay. What about for B? Notice Anderson, they gave me a force and they gave me a test mass at that location, not the planet. I don't know big M. Well, now I'll find gravitational field strength by finding the gravitational force per kilogram. It's going to be 750 divided by 10. You might even be able to do that in your head. Oh, you had me worried for a second there. I was going to come at you. Newtons per kilogram. I can tell you that's not Earth, but I don't know anything more than that. How do I know that's not Earth? What's the biggest we are on Earth for the gravitational field strength? 9.8, and then it gets weaker. Yeah, so there's some mystery planet. Okay. Electric field is very similar. So any charged object is sending out, like the invisible tentacles of an octopus in all directions, an invisible electric field. Small problem. Are you ready? This is your line. Like charges, stuff can fall up. So I'm not going to put down pointing arrows like I did for this picture here. Stuff can also fall down because unlike charges attract. But the same idea, that electric field sits there dormant until another wandering test charge enters it, and then it can be either attracted or repelled depending on the polarity. Example 3 says, fill in the appropriate relationships. The force of electricity is K big Q little q over r squared, where big Q is the planetary charge that's sending out the big electric field, and little q is the wandering satellite test charge that ends up in the electric field. It says definition of electric field. I'm going to come back to that in a second, but the electric field as a ratio, well, the electric field as a ratio is going to be the newtons of force per coulomb. Not per kilogram, per coulomb. Which means if I use the same logic, Alfie, that I did to generate this equation, oh, if you divide by m, the little m cancels. If you divide by little q, what? Oh, I got you just as you took a bite. The little q cancels, Mr. Dueck, the little q cancels. Yeah, you're right. Yeah, the other version of electric field is K big Q over r squared. Can you check on your formula sheet? Did I give you both of these, I think, in the electric section? Yeah. Okay. Although I think I put absolute values around that one, and that's because we're not going to put a negative or a positive in. We'll use that to figure out the direction, but not the magnitude. We want our electric fields to be positive. Definition of electric field, it's the force per coulomb of charge. That's where all this comes from. In the same way, definition of gravitational field is the force per kilogram of mass. What are the units for electric field? Well, we can figure it out right from the ratio. Newtons per coulomb. In the same way that gravitational field had 2 units, newtons per kilogram, which was also meters per second squared. Spoiler alert, it's also volts per meter, but we're not going to get to that. But there is a lot of symmetry here, you may have noticed, between gravity and electrostatics. As I mentioned before, turn the page, I think, as was the case with electric force, we're not going to have negative electric fields. A negative answer simply indicates attraction or repulsion, so don't put the negative into your actual calculations. That's why many textbooks will put absolute value signs around the big Q, and I think I did that on your formula sheet. Yes? Okay. Example 4. Okay. Carter, what's A asking me to find? The magnitude of the mag. What's B asking me to find? The magnitude of the Oh, these must be the same. You know what? Have we just turned the page? Let's write down both versions. So we had electric field, capital E, as a ratio, force per charge, and we had electric field as K big Q over R squared. Okay. Carter, which one do you think I'm going to use for part A? The one on the left or the one on the right? What are the units right here? How do you know? Force, okay? Yeah, don't overcomplicate it. So we can find the electric field, and it says a force is 5.2 times 10 to the negative 4 newtons. And the test charge, I'm not going to put the negative in. I know there's a negative there, but it's not going to be in my equation. It's going to be zero point 0.5. Ooh, Carter, do you remember from the other day? What was that little symbol in front of the C? Micro. This is worth memorizing out of laziness. 10 to the negative 6. What do you get? Electric fields are typically going to be in the thousands, tens of thousands, or hundreds of thousands. If you get an electric field of 0.0003, you're wrong. If you get an electric field in like the 10 to the 10th range, you're wrong. Is this, I'm doing some quick math in my head. Is it 1040, I think? Yeah. Units, Carter. Psst, psst, psst. Carter, what do I measure force in? Carter, look up. What do I measure for? Per? Yeah. Comes right from the equation. As long as I know charge is coulombs, I can derive it. Okay. Direction, I haven't told you that yet. That's why it says magnitude. Electric field is a vector, and the direction is going to be a little tricky because like charges, like charges, and so stuff can fall up. Come back to that. Okay. Joe, what does B want me to find? Which one am I going to use? You know what? Much like Jazz and Deep pointed out earlier, I see meters. I'm pretty sure that's a radius, Mr. Dueck. So we're going to use K big Q over R squared. It's going to be 9 times 10 to the ninth, 2.3 microcoulombs, all over 0.45. Don't forget the squared. Does this work out evenly? No, I don't think so. Joe, let me know what you get. And I think change, yeah? I think this, yeah. Units. Yeah, it's harder to figure out the units from this version, but you got the other version, so don't panic. Okay. Those are the two ways that we can calculate the magnitude of electric field. How are we going to figure out the direction? Again, for gravity, it was easy, toward the center or down. But for electricity, we have the fact that like charges, okay. What we had to do, what we decided, we're going to define the direction. What's the direction? It's the direction that a small imaginary positive charge would go if placed at that point. Say what? It's you imagine a tiny positive charge at that location and you ask, which way would this move if it could? And you figure that out by using like charges and unlike charges attract. We decided to do it in terms of a positive charge. Oh, a tiny positive test charge. How tiny? So tiny it doesn't have its own electric field because that would change the question, which is impossible, but that's why I put in brackets. It's an imaginary, but it's positive. So here's example 5. This is the one that we just did, Carter and I, but I doped. I drew the picture, and it says this: find the direction of the electric field where a negative charge experiences a force toward the south. Well, if a negative charge feels a force towards the south, which way would a positive charge feel a force? B, okay. This is the one that Joe and I did. I drew the picture, and it wants us to find the electric field at this location. If you want to, you can put a little positive right there. Um, Big Q, Joe, positive or negative according to this question? So you can also put a plus right there. How do you know positive? It's because there's no negative in front of it, right? Are these like or unlike? Like charges. Is this going to get attracted left or repelled right? The direction of the electric field at that location is, you could say right or you could say east. I don't care which. I'm better at rights and lefts than easts and wests, so I usually fall back on right or left, unless the question specifically says give it in terms of east and west. In fact, we can draw electric field pictures. This is how Michael Faraday, one of the fathers of electricity, thought of electric field. Michael Faraday was terrible at math. In fact, almost all of his discoveries, he phrased them in English because he just wasn't good at mathematizing them. But he was very good at coming up with clever ways to illustrate things. So this says, draw the electric field around a positive charge. I'm going to draw 1, 2, 3, 4 lines. Could draw more. I'm just going to draw 4. What direction am I going to put an arrow on the upper vertical line? Well, if there was a positive charge along this line, which way would it want to move if it could? Would it be attracted down or repelled away? I don't know what that means. I'm hitchhiking? Yeah, so put an arrow right there. What about on this right-hand line? Which way would a positive along that line want to move if it could? And how many lines did I draw? So in Faraday's notation, if you have charges that have the same number of lines, they're the same magnitude. So if you saw another charge with 4 lines, I'm not saying they're 4 coulombs, I'm just saying they're identical charges. What if I wanted to show a charge was twice as strong? There, now that's a charge twice as strong. 8 lines versus 4. Also, in Faraday's notation, the closer the lines are together, the stronger the electric field of that location, because you're closer to the charge. The further the lines are apart, the weaker the electric field at that location. How can you figure out electric field? We ask, which way would a positive at that location want to move if it could? Says, draw the electric field around a negative charge. Did you add the 8? Did anybody add the 8 lines here? No, you did? Okay. I'm going to erase mine. I'll tell you what you'll do, Anderson, for yours. I'm going to go back to 4 since that's what all of you left it at. I'm going to draw one twice as strong. How many lines will it have then? You're going to draw one half as big. How many lines will your negative one have then in your notes? 4. Okay, so we're all on the same page-ish. 1, 2. Why do I have the arrows pointing towards? Because that's which way a positive would want to move if it could. It would look like that. And I would also, if I saw those 2 diagrams side by side in the same picture, I would say, oh yeah, the negative charge is twice as big, magnitude-wise, as the positive charge. This is a really, really nice little simulator. So everyone look up. I am going to add a charge right there. These are the electric field lines. This charge that I just added, is it negative or positive? And how do you know? Why? Because a positive would want to move towards it. A positive would want to move towards it. But add a second charge and they're going to interact. They're like charges. Like charges repel. Okay? Now what I'm going to do is I'm going to add a third charge, but this one I'm going to make positive, not negative. So you ready? Here's the third charge. Now we get some interesting action happening. Boom, stop. This charge right here, negative or positive, and how do I know? Why? Because the arrow's pointing away. That's which way a positive would want to move. It would get repelled. This one here, negative. This one here, negative. Go again. This is what's going on at the atomic level all the time, this attraction repulsion, especially in gases where charges are free to move around, where atoms are free to move around. Let's add another one. Okay, now we got some action happening here. All sorts of stuff going on. This charge right here, negative or positive, how do I know? Let's see. A positive would want to move towards it. It's not positive. This has got to be negative because the direction a tiny positive test charge would want to move would be towards it, unlike charges attract. What about this one here? Positive or negative? That's a positive one. What about this one? Let's move it over here. What about this one here? Negative. And what about this one here? Okay. So what's the direction of the electric field? We ask, which way would a tiny positive test charge at that location want to move if it could? Which way a positive at that location would move? A tiny positive. How tiny? So tiny it doesn't have its own electric field and change the question. That tiny, which is, again, impossible, but in our pretend make-believe physics world, that's okay. There's a shorter version of this, and in fact, this is what a lot of textbooks say. You can add this if you want to. The short version is from positive to negative. That's the direction of electric field. The only reason, Gibson, I don't go with that is in this picture up here, do you see a positive charge anywhere? You only see a negative. In this picture here, do you see a negative charge anywhere? So it's which way a positive at that location would want to move if it could. If you have multiple charges, yeah, it's from negative to positive. Sorry, from positive to negative. Okay. That was just done as we had to make a choice, and we decided that's the direction a positive electric field will point. What if we have overlapping electric fields? If we have overlapping electric fields, we use something that we call the principle of superposition. It says that if you want to find overlapping electric fields, you find them one at a time, and then you add them vectorially. I like example 6, 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 I like example 6. I like example. I really like example 6. Okay. Gibson, what does example 6 want me to find? Magnitude and direction at that point. How many charges did they give me? What would I do if I was clever before I even started? Do you remember? Yeah, I'm going to go Q1, Q2. Do myself a favor. Q1, Q2. Okay, now I have my idea. Gibson, what we're going to do is we're going to find the electric field from Q1, magnitude and direction. We're going to find the electric field from Q2, magnitude and direction. And then we'll add them vectorially. Okay. How do I find electric field? Well, first of all, which version of electric field am I going to use? Jasmdeep, do I have meters and radii here? Yeah, I'm going to use KQ1 over R1 squared and KQ2 over R2 squared. Okay. K is 9 times 10 to the 9th. Q1. Jesse, put your calculator down. How big is Q1? 1 times 10 to the negative 6. How big is R? 1 squared. Jesse, in your head, what's 9 times 1 divided by 1 squared? 9. What's 10 to the 9th times 10 to the negative 6th? Ethan, don't think I didn't notice that you also used your calculator for this. Really? It's 9,000, I think. Yes? Now, I should point out, Jesse, on a test, Absolutely, I'm using my calculator. And in fact, I'm even typing 1 squared on my calculator, even though I know it's 1 times 1 and doesn't change it. I've made so many dumb math mistakes over the years. I'm paranoid on tests. Units, newtons per coulomb. Direction. So imagine that this one isn't even part of the question. It's not even there. Put a positive right there. Would it get attracted to the left or repelled to the right? Why? Because like charges. Oh, look at you getting your line down. So proud of you. So I'm going to say to the right. You could also say east. Let's repeat. Charge 2. It's going to be 9 times 10 to the ninth. Also 1 times 10 to the negative 6 divided by, what's R2? Don't say 4. What? I will try and suck you into making a silly mistake like that by giving you the total distance and seeing, oh, there's a 4 in the question. I better put a 4 in my work. Yeah. 3. And you know what, Joseph? You don't need a calculator here either, because what's 9 times 1 divided by 9? And then it's just 10 to the ninth times 10 to the negative 6. It's 1 times 10 to the 3 newtons per coulomb. Right, Ethan? You didn't need to use a calculator for those at all, did you? Direction. Okay. Imagine, again, pretend this guy isn't part of the question at all. Which way would a positive sitting right there move because of Q? The 2 vanished. Attracted right or repelled left? How would I add 9,000 right and 1,000 left? Be stupid obvious. Yeah, winner minus loser, which is what I snuck in Physics 11 with that shtick. Yeah, you want the net electric field? It's going to be 9,000, take away 1,000. Jesse, I bet you can even do that one in your head. Newtons per coulomb, or 8.00 times 10 to the third. And what was the winning direction? Right. I could give you 3 overlapping charges. Not a problem. Do each one magnitude and direction, add them vectorially. I could give you them at right angles to each other. Then you would have to add them. How would you add 2 vectors together? Draw them. Yeah, I'm not going to hit you up with that. I had to make an executive decision to cut corners to get more material in. So it's cool, but Example 7 says draw approximately the resultant electric field at the indicated points. Both of these are identical positive charges. What would the field be right here? You know what? I got a sim for that. Kind of convenient. So here's a positive charge. Here's another positive charge. What's the electric field right there? Why? Because the one charge is repelling this way, the other charge is repelling this way. They have the same magnitude. In fact, I have electric field sensors right here. They show me the electric field. You can see it's all over the place, but right here, halfway between them, what's the electric field? 0, because the net field cancels out. Does that make sense? Okay. So we can leave the middle blank. What about right here? What's the net electric field direction? Now, how can I explain that? What I really have right here, just look up, this is pushing really hard to the right. This is repelling a little bit to the left. Oh, you know what I should have done? First thing, Q1, Q2, because now I don't need to say this is, and I can use terms. So Q1 is repelling to the right. Mr. Dueck, wait a minute. You said Q1 and Q2 are the same size. How come Q1 has a stronger electric field? Radius, yeah, we're closer. Okay. So if you have hard right plus little bit left, what's your net result? Still mostly right. So that's why in my sim, I get that. What about over here? Same idea, yes? We would have Hard that way, little bit that way, but the net result would be to the left. Alrighty. What about right up here? What would you expect? Well, this one would be repelling it this way. This one would be repelling it that way. How might I add those two together? Draw them. Yeah, wonderfully, I can even do that with technology. I can click on this and I can go d d d d d d d d d d d d. What direction does the resultant look like it would point? Straight up, you say? Let's go check out the sim. So what you're saying is that if I go dead between them, the electric field in the middle should be like straight up? Is it? Yeah. Now the last spot they went with is right here. I guess here it would be repelling that way. This would be repelling a little bit that way. Again, if I add them tip to tail, I guess the resultant should be mostly up, but a little bit sideways. Let's go check. When we're directly above the left-hand charge, is it mostly up, but a little bit sideways? Yes, it is. Okay. Example 8 says, draw the electric field pattern for equal like charges. Okay. These are both positive, and they're both like. So what will the field be right in the middle here? In fact, if I draw an electric field line, it would start like this and it would get repelled away by the other positive. It would start like this, they'd be symmetrical. How do I know they're symmetrical? Equal like charges. Why did I put the arrows pointing away? That's which way a positive would want to move if it was sitting on that line. You would have another line that would kind of start this way and get repelled that way, another one that would start this way and get repelled that way. You would have another one down below, something like this. You'd have another line like this. And you can just keep in filling a bunch of more lines. In fact, I got some good software. I found a nice diagram. If you want to know what it looks like between equal like charges, you stay where you are. It would look something like this if you keep filling in more and more lines. I'll come back to that in a second. What about equal and opposite charges? I'll do that in red just so you can distinguish. Well, this one would be definite. Yum, whap, right across. A positive would get repelled and attracted. Whoop. And then amber, if I left right here, I would get sucked in there because that's which way a positive would want to move if it could. Get repelled and attracted. If I went straight up, I would probably end up there. If I went straight down, I'd probably end up there. Usually right around now, I say it kind of looks like a frog with big eyes or something like that. That's one of the ways I know I'm doing it right. But again, there would also be a line that might leave there and it might come back on there, going way out. Because electric lines do technically, electric field lines, they technically go out to infinity, but of course they get weaker and weaker, so there comes a point when you just don't care. How many lines did I do on the positive? 1, 2, 3, 4. How many lines did I do? 1, 2, 3, 4, 5, 6. You could say, you could assume if these are part of the same picture that the negatives and the two bottom charges were higher magnitude than the two upper charges. So the idea of the electric field originated with Michael Faraday. I told you, great experimentalist, terrible at math. He was in the he basically was in the 1800s, which is the 19th century, and he is the father of electricity. He used lines of force which showed the direction in which a positive test charge would tend to move if it was placed in that field. In other words, if I go back to this diagram here, if this was a positive charge, oh, I got a sensor out there already. A positive charge right here would go, oh, you know what? Let's bring a negative charge in instead, unlike charges. So a positive charge right here would follow, and end up like that. It would follow the arrows. Here it would go, it would vanish off the page and come back on. So this shows the lines of force around a positive test charge, around a negative test charge. Are these charges the same magnitude? Yeah. How do I know? Same number of lines. Here is one with positive and negative, so opposite charges. Here is one with two positive charges. I won't be asking you to draw electric field lines per se, but these make great multiple choice questions. You can imagine if I gave you this question but had that colored and said, is the left-hand charge positive or negative? Is the right-hand charge positive or negative? And so your choices would be positive, 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 negative, 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 positive. What's the correct one? You can figure it out. Or some other combination. There's a number of those in your ultimate review. You'll see them. Example 9. I I I think I like example 9. I can't remember. 3 charges. Oh, I labeled them. Yay! What am I going to do? Well, first of all, Adam, what does it want me to find? I'm going to find the electric field from Q1, the electric field from Q2. Oh, magnitude and direction for both of those. Electric field for Q3, magnitude and direction. And then I'll ask which one is the biggest, and I'll add them vectorially. I can do this. Okay, so the electric field from Q1, I'll call that E1. It's going to be K Q1 over R1 squared. It's going to be K. Adam, I've scrolled down. What was Q1? 12 times 10 to the negative 6. All over. What's R1? Really, dude? I can't believe I got you there. Look at the picture carefully. What's R1? How far is Q1 from point P? Yes, 1.55. I guarantee I will try and trick you like that. And in fact, I'd probably, if it was multiple choice, make that answer A, just to really taunt you. All right. The nice thing is these are repetitive enough that once you type 1, you can usually backspace edit and just change the numbers quickly. I got 44,950. I'll go to 4 sig figs for now. 4495 newtons per coulomb. Direction. So imagine the middle charge isn't part of this. Imagine Q3 isn't part of this. A positive sitting right at P, will it get attracted toward or repelled away? Would it get attracted to the left or repelled to the right? Well, this was positive, so you were right. Repelled right. Yep. So right. Now I'll find the electric field from charge 2. It's going to be KQ2 over R2 squared. It's going to be K. I've scrolled down, Adam. What was Q2? Oh, that one is 0.8. And I can just backspace, I think. Instead of a 12, you know what I can do? 0.8. That one I don't have to delete the 2. And then 0.80. That'll work. I get 112,500 for the second one. Direction. Which way would a positive at point P want to move because of Q2? Attracted left or repelled right? Also right. Q3. And so, as far as I'm concerned, Chantel, I can give you 4 or 5. I'm not going to, but I can give you as many overlapping electric fields as we need, right? It's going to be KQ3 over R3 squared. K, what was Q3? 15 times 10 to the negative 6, all over 1.2 squared. backspace, edit, 15, 1.2. You get 93,750. Is that right? Yeah. Direction. Ah, this one's to the left. Face down on the appropriate block, please. Then you're good. How will I add 48,950 right plus 112,005? Well, what direction is winning pretty clearly. So I'll call that positive, call the other one negative, and we'll do our usual winner minus loser shtick. So it's going to end up being, what's the net electric field or the total electric field? It's going to be 112,500 plus 44,950 minus 93,750. What'd you get? 63,703. Were you using you used your answer button? Okay, so 700 then, right? Okay. Newtons per coulomb. What was the winning direction? Right or east, whatever you want to let it be. So this is our explanation for action at a distance. All charged objects are touching each other. They're just touching each other with an invisible meter stick, not the one that I was poking Riley with. Field theory is one of the more recent branches of or philosophies of physics that explains a lot. If you dive into physics in university, you'll talk about energy fields, Higgs field, electric field. It really is how we explain a lot of what's going on. Here's our summary. The electric field can be found using the definition. What's the definition? Newtons per coulomb. The units. Force divided by charge. That's if we know the force on a test charge placed at the field point. It can also be found if I know the planetary charge that's creating the electric field. That's going to be K big Q over R squared. I didn't put vector signs. Oh, I did put a vector sign on both of these. They're scalar equations. How do I figure out the direction? Which way would a positive at that location want to move if it could? Or Carter, away from a negative, away from a positive, wow, towards a negative. How can I find the force? K, big Q or Q1, little q or Q2 over R squared. But there can be a shortcut if you keep your eyes open. How would I get this F by itself? How will I move the Q over? If you happen to know the electric field at a location and what charge is at that location. By the way, you know what that's electricity's version of? Fg equals the obvious one. That's the electrical version of mg, the shortcut for gravity if you happen to know the gravitational field strength that we used in physics 11 all the time. So you're noticing a lot of overlap between gravitation and electricity. For electric force, it's not which way would a positive want to move if it could. We use like charges repel, unlike charges attract. And for both of these, since they're both vectors, if we have multiple values, we add them vectorially. Okay. What's your homework? Here's the ones that I assigned, and then I need to apologize because I'm about to give you the most addictive bonus ever. I want to get to block G, Mr. Dueck. That's what I just taught. Sorry. So, try number 2, try number 3. Skip 4. 5 and 6 are good. You can skip 7 and 8 and 9. 10 is kind of cool. Try it. It's going to be a job for a free body diagram. In your free body diagram, gravity is pointing down electric force is pointing up. You'll have to figure out who's winning by just calculating each of them. And then once you do that, that'll give you the net force. And then find the acceleration, find the final speed, find BF. How would you find the acceleration? F equals what? MA. 11 is good, skip 12. 13 is good, skip 14. 17 is good, skip 18. 19 is just a nice little brain teaser. I'm not going to ask you one like that. Okay. But before you go any further, could you please, where the note's finished, could you write bonus for test, Google PHET, electric field hockey. This is your bonus challenge. I'm going to pause the video right now. If you're in my class and you want more information, you'll need to come see me in person.